Yes.
Okay. Hi guys, welcome to the Python workshop by MTRN4110. This will go through some basic Python if you haven't done 1531, and we'll go into some more advanced stuff by Tanvi in the second half. Okay. This is the code repo if you want to look at it later. These are the topics which will be covered. Okay. What is Python? Python is an interpreted language, which is where the source code is converted into bytecode and then executed by a Python virtual machine. It is compiled differently compared to C++, I guess. It is also object-oriented. Everything in Python is essentially classes. It is dynamic typed, which means that you don't have to initialize a variable with one specific type. You can choose to change the type of the variable as you go on. Garbage collected, meaning you don't have to malloc any memory. I guess Python does the memory managing for you. Yes, and then it's a scripting language, and they also use white spaces instead of squirrely brackets for any, like the if statements and like the functions, I guess. Okay. Variables and types. Python is a dynamic typed. Well, Python is dynamic typed, which means that its variables, parameters, and return values of a function are not specified at runtime. And you can basically just assign a equals to 1. Python will interpret 1 as an int, and it will set a to be an int. Similarly, if you assign b to be 1.0, it will determine that to be a float. Python doesn't have the type char, so if you want to set it to one letter, it will determine that to be a string. Similarly, for the D variable, it will set that as a string variable. And then it also has type bool, which is true or false. You can see the type of variable it is by printing type A, or you can print A by itself by printing just to print A or print B. Python will print that variable regardless of whether it is a string or not. Okay, strings in Python are immutable, which means you cannot change it once it is initialized. There are many different ways of formatting strings. And you can print it using the plus sign, which basically concats the name, which is a string, and then you can add like a string to the print function by itself. And you can also print any variable, but you have to convert it to a string so that it can concat properly. Yeah, basically that's it. And there's also F strings in Python, which means you can print the variable itself without having to convert it to a string. You just dump it in there. Python will interpret that for you and it will print it. There are also many different types of built-in string methods that you can use. For example, you can print the first letter in a string by itself by using the index, which is index 0 for the first one. Or you can go from the negative side, which means from the end of the string, and do -3, meaning the third last character. You can also split up the string and specify where you want to split it. For example, here you want to split it where there is a space, which means it will find all the spaces in that string and it will separate it there. And then it would print hi, and then from, and then matron-sock. Okay. And then there is this way of printing where you specify where you want the string to start, where in the string you want to start, where you want to stop, and the step it takes, which is the number of jumps while going from start to stop. Conditions in Python are essentially the same, except instead of using the double ampersand or the double and sign or the double like 2 vertical lines, you use like the word and, and the word or and the word not. I guess it's easier to the eyes to read it. That is basically the only difference. You still use it the exact same as you would in C++. Okay, in Python, instead of arrays, there are something called a list, which is an ordered collection of data. They are basically, you can think of it as dynamically sized arrays, where you don't have to initialize the size. You can keep adding to it as you go. And yeah, it's basically how you would use it in C++. You can use the .append to add a value to it. You can print it using a for loop, which we will get to later. Yep. Okay. So here there are different ways you can loop through a for loop in Python. It is similar to C++ in the sense that you can go from each index as well. Or you can go through each variable like I did here for name in names, where names is a list and name will be each variable in the list, right? Python, I guess, finds it for you and it will print it accordingly. Tuples are a way to store multiple items in a single variable. They do not have to be the same type of item. You could store like a string and then a bool or like an int. But once you create it, they are immutable. You cannot change the values. To change it though, you can convert the tuple to a list, which you saw up there somewhere. Yeah. Other than that, you can print it how you normally would with other variables, and you can access it how you normally would with list as well. They're usually used for when you have to return more than one value in a function. Okay, functions in Python are pretty much the same as C++, except you do not have to determine the type of the parameters and the type that it returns. See here, there is no type, there's only def and a colon to determine when the function starts. So here you have the arguments x and y. Z equals to x plus y, which returns the sum of it, and then you return z. You never specify that z is an int. So technically you can have x and y to be a string, and it would return the concatenated version of the string. But when you do want to know what the type is, you can use this syntax where you have an arrow and then an int. Just for yourself to know, the interpreter doesn't actually get this information. If you have a function definition with no content, you can use the pass keyword to avoid getting an error, which is essentially you type, instead of this, you return, or you type pass, and then it will just move on. Dictionaries is a way to store data in Python. It has key value pairs. Unlike lists and arrays that are referenced by their integer index in C++, dictionaries are referenced by their key that maps to a value. They're similar to maps and unordered maps in C++. Okay, see here, you add a key value pair like this. The key is the name and the value is where you assign it to equal to. You can add strings, you can add ints, all types of values, but the key has to be a string. Yep, and then you can print it like that. It prints like this. Alternatively, you can also initialize a dictionary like this. Basically type everything you need in the dictionary, and it initializes the same. Wait, can you have ints in as a key? Oh, okay. You can also have ints as a key. Ignore what I said earlier.
Yeah, a key can be of any type.
Oh, okay. A key can be of any type, and the value can also be of any type. Okay. To get the value in a dictionary, you can use the .get function to fetch the data. It takes one argument and an optional argument, which is the default value to return if the key is not found. So here you use the .get function, and the key here is name. it will look up where the name is in the user data dictionary and it would return Janice. Alternatively, you can use .get and then input the key you want with the return, what you want it to return on default. So it would loop through here, look for ZID. There is no ZID. So therefore it would return the default, which is none. Okay, to loop through the dictionary, you can use this for loop, which is for key and value in user data.items. And this will return, well, it will store the key value and the value in the dictionary per each data set, I guess. What is this? Okay, it destructures whatever is here into a tuple and it stores the first item in the tuple as a key and the second one as a value. Yeah. Okay. Type hints. This was what I said before about the arrow pointing to the variable in a function. This is optional. You don't have to do it for every function. They don't do anything when you run the code and they're ignored by the Python interpreter. They're only used by code editors and the type checker called MyPy. But it's just for, I guess, for you to read your code a bit easier, for you to know what it actually returns. Yep. Okay, it should error when you return something that's not an int. Okay. You want to take over?
Okay, so there are fancier methods of basically including types for in Python. So there's this typing library that basically you're able to import all these different types, I guess. So for example, if I wanted to describe a dictionary, for example, I would import dict from typing. In this case, I have this is a class, but don't worry too much about the syntax, but basically I have a flags variable and I basically want to set this to be a dict that maps strings to booleans. This is generally how you would do it using the imported dict from typing. Similarly, in line 4, when we have numbers, I want it to be a list of integers or floats. And how you would do that is you would import list and union. So list obviously describes a variable that's a list, and then union is sort of like a or. So basically, if a union between int and float is this variable can have integers or floats inside of the list, and this is generally how you would do it. There's also another thing I like to use called optional. So if a variable can be none, or null, basically, it's a good idea to set your type to be optional, just in case you try and call a method on this variable. If it can be none, then you'll get some sort of null pointer error. So setting it to be optional is a good idea. So it basically prevents you from writing bugs or causing errors with your code. So another good part of Python is modules. Basically, each Python file is its own module. So in this case, we have 3 different files. We have add.py, mathsolvers.py, and calculators. So each of these files that are pretty much their own modules, and they're basically defined by their file name. For example, add.py, its module name would just be add. Similarly, mathsolvers.py would just be mathsolvers. Whenever you write functions or any variables in the global scope, these basically all get exported as part of the module. So in calculators.py, I can import add, which basically imports everything in the global scope, defined in the global scope. And this would allow me to basically use the add function defined in add.py inside of a different file called calculator.py. So for example, in line 1, I've imported add, and in line 8, I'm using add.add. So the first add refers to the actual module name, and then the dot refers to like a method inside of this module, and the second add is the actual function name, right? And then I'm just basically passing in 1, 2, and this would just basically add the numbers. Similarly, in mathsolvers.py, I have multiple functions defined in the global scope. So in this case, I have subtract and multiply. A different way of importing is using the from something import something or something else. Okay, so how it works is from module, I import a bunch of functions or variables. So in this case, from math solvers, I'm importing the subtract and multiply functions, and I can just directly use them by their subtract and multiply because the scope is already defined, since subtract basically comes from math solvers that's known from this import. The from import, the from module import syntax is much more preferred, since in the first type of import, you're basically importing every type of function that's defined in the global scope in add.py. Whereas in the second type of import, you're only importing what you need to use. So this might make it more efficient in the case where, you know, add.py has quite a few functions defined in its global scope. Another important thing is to note is when you import a module from another Python file, it basically attempts to run all of the global scoped code. So global scoped code basically means something that's not wrapped. So any code that's not wrapped in some sort of function or if statement. So in this case, in file A, I have a function called def do something A. This function is just defined in the global scope, but the code inside of it, which is the print that I currently highlighted, is not in the global scope. It's scoped under the do underscore something underscore A method. Function. Whereas this print statement in line 4 in file a.py is part of the global scope. So obviously when I run Python Python a.py, this would always print no matter what. And this function won't run since nothing is basically calling it. Similarly in Python, in file b.py, I have a function called do something b, which just basically prints a different string. And I have this special if statement here. So generally any variables that are underscored twice are sort of like custom or special Python environment variables. So in this case, underscore name and underscore again. Basically, that's the name of the module that I guess the code is running from. So when I run Python 3 file b.py, as seen in the bottom part of the screenshot below, underscore name will basically become underscore main because that is the main file being run. But if I checked underscore name in like file A, it wouldn't be underscore main, it would probably be file A because that's the module name. So basically what this if statement does here is it only runs the code inside of this if statement if the file is directly, directly run by the Python 3. And the reason why you would want to use this is to prevent globally scoped code from running when you import it in some sort of other, other file. So in the example of controller.py, I'm importing both file A and B. So when I import file A, it'll basically try and run, it'll basically look through the whole file and it'll run any globally scoped code, in this case, which is print, global print from file A. And we can see that being printed in the screenshot, in the top half of the screenshot. We can see global print from file A is run, but when we import file B, the print statement inside this the print statement inside of this if condition is not actually printed because on the underscore name in this file B would have been probably file B, the module name, and not underscore main. Hope that made sense. But basically include this if statement for any globally scoped code if you don't want it to run when some other file imports this module. So one of the other great benefits of using Python is the availability of published packages. basically you can probably find a package for just about everything you want to do in Python. Like there are packages that deal with time and like time zones, which is annoying to deal with, but people have like made packages for that. There are packages for doing scientific programming. For example, NumPy and SciPy. SciPy, I think, has a lot of math algorithms. So maybe if you're doing a lot of linear algebra, NumPy and SciPy might apply to you. There are also other packages like Flask, which is more intended for like web dev, like web servers. And there's a package called MyPy, which we've sort of breezed over, sort of used for type checking. And yeah, so these Python packages are basically hosted online, and we can install them using something called pip3 or pip. Generally, because Python has like two known versions, is Python 2 and Python 3. Pip3 refers to like basically the Python 3 version of pip, and generally pip on its own would sometimes refer to Python 2, but it really depends on your Linux operating system or whatever operating system you're using. So pip3 and pip can sometimes mean the same thing. It really depends. You just have to check the versions of pip or Python. So you can basically find these packages by just Googling online. Like, for example, you just Google NumPy and there's like a whole website for that. And we can install these packages using pip3, using this command. So it's basically pip3 space install space and then the package name. So when you install stuff using pip, generally they're installed globally. So probably at like the root of your file system somewhere. And this is sometimes not useful because we want to separate our Python environment for like different projects. So for example, in your 4110 project, you're going to use like probably a few packages, but then like if you're working another course, they might not need those packages and they might need separate packages. So separating or creating isolated Python environments is very useful. And this is usually done through a package called virtual env or virtual environment. The env just stands for environment. So to use virtual env, we can basically install the package using pip3. So we do pip3 install virtual env. This will install the package globally, which is what you want. Okay, there's a line missing here. Okay, so that's how you would install virtual env globally. And another command to actually use the virtual env would be actually, you would have to do something like Python 3-m virtual env. Let's see if I can type this in. Let's see. Okay, no, I can't. But basically the, let's Google this. Okay, so let's see, virtual env. Okay, not exactly what I want, probably this one. So generally how you would use virtual env is, this would probably be a command that works, but you can also probably use something like this. So you go Python 3-m, and this would probably be virtual env instead of venv, but I think it works anyway. That's like the shorthand version of it. And then the string you put after here is basically the path that, that like, I guess the virtual environment is placed into. It's like some sort of folder. So in this case, I named the file venv. So in this case, I would put Python 3-m virtual env, and then the string here would simply just be venv/. That would be the path of my virtual environment. And after you run that command, it basically created the isolated Python environment inside of that folder. And in order to actually use the isolated Python environment, you have to use this source command. So in this case, it's source, and then the first bit would be the path to the folder that you've just created, and then it would just be /bin and /activate. What this does is basically just change all the environment paths to just basically use this virtual, this isolated environment that you just created. Don't worry too much about like how it actually works. It's just every time you open a terminal, you have to run this source command in order to basically tell your terminal or your to basically tell your terminal to use this isolated Python environment instead of your global one. So now that like projects can have different modules, there becomes a question where like, how do you know, how do you make sure that like, you know, the person running my code would also have like the same packages? So this is sort of accomplished through a text file called requirements.txt. It's just simply a text file that basically names the packages needed and the versions of the packages needed to basically run your code. So this is pip3 freeze command, where it just basically, I guess, it looks through your installed packages and basically dumps them into like into a requirements.txt folder, requirements.txt text file. This is how you would basically dump like this. So in this case, this is what a requirements.txt folder looks like. So for example, in this case, I have a package called MyPy and its version is 0.961. So this is dumping whatever packages I've currently installed using the freeze command into this requirements.txt file. And then this is what you would probably give to like someone else in order to run their code, in order to run your code. And what they would do on their end is they would have to install all these packages in this requirements.txt file using pip. And how you would do that is using the install-r flag. So the command is pip3 install, and then you have the r flag, and then you give the path to the requirements.txt folder, and pip3 will basically loop through this file line by line and install all the packages needed to basically run your code. So that's how you handle version control, I guess, with your packages using pip and requirements.txt. I believe we're going to take maybe a 5-minute break, and Tanvi will continue the presentation for NumPy.
True. iPhone 5, I guess. Okay, so I guess I will. Can you guys see my screen all right? Yes. Cool.
Yes, we can.
Okay. I guess I'm gonna just talk about NumPy and Jupyter notebooks and maybe OpenCV. Probably not OpenCV. Yeah, we'll talk about NumPy, which is a Python library that gives you a lot of versatility in working with arrays. So yeah, obviously Python has a bunch of great standard libraries built in for like things like lists and dictionaries, but lists are sort of limited in what you can do with them, as in they're great and versatile and they're a lot easier to use than like C arrays, but we can do a lot more with them with the right interface. And so NumPy is an external library that gives you access to basically like a super powered list. They call it a NumPy array. It's super useful for all kinds of different things. So yeah, NumPy is a Python library for working with multi-dimensional arrays and matrices. It's very easy to use and it's feature packed. It's a very huge library in what you can do with it. And the other nice advantage to it is that most of the algorithms are written in C. And so while you'll be using the interface in Python, all that precompiled C is going to make your programs run a lot faster. Okay, so NumPy arrays and lists. So a few advantages that you get with NumPy arrays is that they use significantly less memory than just regular Python lists, especially in higher dimensions. there's a lot of overhead when it comes to Python list and a lot of basically not unnecessary, but inefficient use of memory. So NumPy arrays are highly optimized for space. And again, because most of the array functions, NumPy array functions are going to execute from compiled C, they operate significantly faster than Python list operations. Another huge advantage of NumPy is that many other external packages also use NumPy. So things like SciPy or OpenCV or even Pandas, they all use NumPy under the hood because of how well optimized it is. Basically, everything's super compatible with NumPy arrays, and you should definitely be using them constantly. One, not really a disadvantage, but one of the caveats to the optimization of NumPy arrays is that they cannot store different types in one array. So with a regular Python list, you can have a list that has like a string and then also an int and then a bool and whatnot. You can have all different types in there, which is, you probably shouldn't be doing anyway, but I mean, it's a feature that exists for Python lists. But yeah, for NumPy arrays, because they're highly optimized, they do require you to have just just the one kind of type in your NumPy arrays. We'll go through some examples of how to actually use NumPy arrays. This is a very basic thing. So of course, you're gonna have to import the library. As standard, we do import it in this fashion where we say import NumPy as NP. Most of the code that you see online, most of the example code will use this import style because NP is just like the the standard way to refer to NumPy. So yeah, we can do things like creating the array. It is a bit more complicated than creating a list, but basically all you have to do is call this NumPy function called array. So you do np.array, call this function, and you pass it you can pass it a regular Python list, and that will convert that Python list into a NumPy array. Yeah, it's a very simple operation to have a Python list and turn it into an array. If we printed the type of that list, it would come up as a ND array with the, well, yeah, if we print it, it would say ND array and then int something. So it would tell us both the type of like what it is, so it's an array, and also tell us the type of what it's storing. And if we printed the shape, the shape refers to how many dimensions and how big each dimension is of that array. So of course we can have multi-dimensional arrays. In this case, we have a one-dimensional array that is of length 1, 2, 3, 4, 5, 6. So it would just print 6. Yeah, this shape attribute is, if it's a higher dimensional array, it will be passed out as a tuple. If that's necessary to know. So if you have like a 2-dimensional array, it would say like 5 by 6 or something like that in like a tuple, 5, 6. Yeah, and we can also access items in the array the same way we would with regular lists. So using our square brackets and indexing at a particular place. Slicing is also exactly the same. So we can do regular slicing where we would specify the start, stop, and the step. That works just fine. And again, here's an example of a 2-dimensional array where we specify that our we actually give it 2 arrays in a tuple. You can actually put it in as a list of lists as well if you want. And this would give a 2D array of this 1, 2, 3, 3, 4, 5 stacked on top of each other. You can sort of see it. And we can access those 2 dimensions the same way we would a Python list in 2 dimension with, again, 2 sets of our square brackets to index into those positions. So there's a bunch of different ways to create arrays in using NumPy. So obviously the one that we've shown already is the passing in a Python list, which is a pretty convenient way. Other ways to initialize them is zeros is a really popular one. So np.zeros lets you create a array that's just filled with zeros. So you just specify the size of the array. That's the first argument. You can pass. So in these examples, I've just passed in. Here I've passed in a 2, and that's just going to create a one-dimensional array of size 2. So you can see here it's just basically going to be 0, 0. If I was to do like 2, 3, then it would be a 2 by 3 array of zeros. So we can pass in the side or the shape that we want it to be, and this function will create us an array of that shape. Same thing with ones. Instead of filling with zeros, it's going to fill with ones. We also have np.empty, which I haven't put the output here because it's going to change each time. So empty is going to initialize an empty array. It's not actually empty, but it is just filled with random values or just like random memory from wherever it was pointing at, basically. So it's not empty, but it's doing the same thing where it'll create you an array of that shape with some data filled in. We have a range, so similar to the Python range function, we can specify a start, a stop, and a step. And that'll create us an array based on that. And you can also use that in for loops as well if necessary, but probably not necessary. We also have linspace. So if you've used MATLAB before, you should know what linspace is, hopefully. But basically, it's going to say all this does is creates an array with linear spacing. So you have to specify the start, the stop, and how many items you want, in contrast to like the step. So in this case, if we're going from 0 to 10, and we want 5 items that are linearly spaced between 0 and 10, we're going to get 0, 2.5, 5, 7.5, and 10 in an array. So yeah, there's a bunch of different ways to create arrays. There is a bunch more, and I'd advise you look at the documentation if you need any more than this, but I think usually just zeros, a range, and linspace covers most of the cases that you would need. But of course, there's more if you need them. Okay, some basic array manipulation. I'm not going to get too in depth with array manipulation because there is like tens of functions that you can use, probably like so many that I do not know them all, and we can look them up in a sec. But some basic ones, we can do some array sorting. We can concatenate array. So array sorting is just using np.sort. There are a bunch of different sorting algorithms, some that work in place. So that's operating directly, sorting the array that you pass it, and sorting inside that array, and some that don't work in place, so that create a copy of an array. So np.sort actually creates a copy, sorts that, and then passes that back out so that your original array doesn't get affected. Again, if you use an in-place sorting method, then your original array will be affected. Yeah, there's different algorithms that you can use for that. For concatenating arrays, you use np.concatenate, which you have to pass in tuples of your arrays, and it will concatenate them. So if I don't have the output for this one, but if we concatenate the original AR and the sorted array that I made, then we'd basically get this plus this, so it'd just be 2, 1, 5, 3, 7, 4, 6, 8, and then that would continue on to 1, 2, 3, 4, 5, 6. So just be a really long one-dimensional array. We can, of course, concatenate in different axes. So if we want to concatenate along a different axis, we can specify which axis we want to concatenate. So here I've got a 2D array that is called X, which is just 1, 2, and then 3, 4. So that's 1, 2 in the first row, and then 3, 4 in the second row. You can think of it like a matrix. And then I've got my Y, which is just 5, 6. And if I concatenate those on axis 0, that's just saying concatenate down. It will create a matrix that is a 2x3 matrix. You can see the output there. Yeah, again, there is a ton of different array methods. If I take an NP array methods, we have a look at the documentation. So it's called a array, or NumPy ND array is the actual name, but we just call them arrays. And you can see, if you go to the methods, there are a lot of methods to use. I use another useful one here is toList. So that's just creating a Python list out of the array that you're giving it. Reshape and Ravel are really good. So returning a flatten, Ravel returns a flattened array. So if you have a multi-dimensional array, you can flatten it out into a single dimension. Yeah, there's lots of useful things. Yeah, like min and max, mean. So things like that. Yeah, there's lots of math ones as well. So cumulative product, cumulative sum. Go through that. Some of these will be useful, some of them won't be. But yeah, there's lots of different methods on arrays that are built in through NumPy. I will go on to the next. Ooh. Okay, Jupyter Notebooks. Yeah, let's move on to Jupyter Notebooks. So this is a bit of a departure from what we've just been talking about. A Jupyter Notebook is basically a way to run Python that's sort of not your typical write it in a file, execute the file, write a bunch of functions and have those functions execute. This is a bit different. So a Jupyter Notebook is a way to write Python code, or not necessarily Python code, but usually Python code in a way that is very human readable and is generally not designed to be a sort of standalone program. It's meant to be a a bunch of code, but also a bunch of rich text elements, or basically just text to describe what that code does. It is super useful for scientific and engineering use. A lot of data scientists use it. Anyone who's like in a scientific or a research context generally uses Jupyter Notebooks as a sort of playground for experimenting with different bits of code to do different bits of analysis on data. They're aimed to be human readable documents that contain both the analysis description and the execution. I've got a picture here that's not fantastic, but it's based, I'll bring up the actual notebook here. So yeah, this is what a notebook looks like in Visual Studio Code. You can open these notebooks in all kinds of different editors and IDEs. I do prefer Visual Studio Code. There is like a Jupyter Notebook IDE that it sort of ships with, and that's convenient to use. But basically all it's made up of is different cells. So this top one here, which I've just now sort of put into its edit mode, is a markdown text cell. So all it means is that I can write some text in here, and using markdown, which is just a special way of writing text or formatting text, I can do things like give it titles, make it bold or make it italic and whatnot. And then once I've written my description, hello there, this is cool, I can make it italics if it wants to go italics. And if I hit the tick, it renders. So my big title is there. This is a file to demonstrate how Jupyter Notebook operates. And hello, this is cool. And you can see that Jupyter Notebook and cool has bold and italics for formatting. And yeah, it's meant to be human readable, right? And then, so that's a text cell, but we can also have Python code cells that can run and execute on their own. So this code cell is very simple. I've just imported NumPy. and I can create a 2x2 array of all zeros. And each cell has its own little play button, which I can hit to run that code. There's that. You can see here that this tick has said it's run successfully. It only took 0.2 seconds to run. But that's about it. There's not much going on here. If I wanted to print this out, so if I wanted to print A, I can do that as well. Run the cell again, and this time it prints it right below the cell itself. So you can see here I've made a 2x2 matrix of zeros using np.zeros. Now, this is all well and good. I can create more cells. If it lets me create more cells, I can create more code cells and write more code here. I can create more markdown cells and write more text here. More text. I can write more code here. Now, the really cool thing about this is that the way a Jupyter notebook works is that it has what's called a kernel running. So what this kernel is doing, do I have the slides? Yeah, what the kernel is doing is when a notebook runs a section of code, the variables that are created or manipulated are all stored in memory, in the kernel's memory, and those variables can be used across code segments or code sections. So yeah, the kernel manages all these variables and the Python environment. So basically, this A variable that I've created here in this cell, I actually have access to it here, so I can print it here. That's cool. And so basically this A variable exists. Once I've run this code and I've instantiated this A, it exists in all my other code cells. And we can see here, there's a variables button here. If I click on that, it gives me a list of all the variables that the kernel currently is tracking. So if I wanted to make a new variable, say b is equal to a, but only for the values that are greater than 1. So I hope that's going to execute. We can see that b gets created as well here, which is also an array. And you can see the value here as well. If I double click this, the data view will come up. Oh, God, is that going to even work? There we go. And you can see what's inside it, which is just a bunch of falses because nothing in A is greater than 1. So yeah, you can sort of see how this is super useful, that you can see all your variables as you run them. Now, if you might see that this is very similar to something like MATLAB, where MATLAB also stores all your variables and you can sort of manipulate them as you want. And it's really similar. Like you can, like these are just different code sections and you can have just text in between them. Super useful. You can also restart your kernel, which will basically, it says here, do you want to restart the Jupyter kernel? All variables will be lost. So if you restart your kernel, you are going to lose all your variables. So now there's no more variables to find. And you can see if I try and run this section where I try to print A, it's going to give me an error. It's going to say name error. A is not defined because even though, because I'm running this section where A hasn't been defined here, and I haven't run this section where A is defined, it's going to give me an error. So I definitely have to run this section first, get a success there before I can run this section. Now you can see that's a really good way to segment your code and sort of experiment with things as you need to. I'm probably not going to go through all this. What time is it now? It's 4:05. Oh, okay, we can go through it. So this is just some more NumPy examples, similar to what we've already looked at. So you can see we can run this section. So this is like the first slide from the NumPy that we looked at. So we can create an array. We can print the type of the array, and you can see here it's a NumPy ND array. We can print the shape. Here it's giving us 6 comma, so it's basically saying it's a one-dimensional array with 6 items in it. If I wanted to do, wait, I do it like this, if I change this to, actually, let's just print this one. Print, it's called list 3. Dot size, dot shape, sorry. Let's run that again. You can see that when I print the shape of this one, it's 2 by 3 because there's 2 rows and 3 columns. So it's a 2 by 3 matrix, basically, or 2-dimensional array. Yeah, I mean, that's NumPy and that's Jupyter Notebooks. Very useful. And again, you can see our variables are popping up down here as we run them. We do more zeros and ones. Again, they're popping up down here and we can see exactly what's inside them. If you're working with big data sets, this can be really useful because basically you don't have to reload all your data all the time when you run a file, which if you're working with big data sets can be very annoying if it takes like, you know, the 10 seconds to read in like a 200 megabyte file. With Jupyter Notebooks, you can just read it in once, it's stored in your kernel, and it's ready to access in your memory at any time. I think, okay, we can go through the rest of this NumPy stuff because it is pretty useful. Boolean array indexing, this is something I've just like shown earlier in my thing where you can take a NumPy array, you can do a Boolean operation on it. So you can say, oh, list 2, what was list 2? It was just this set of numbers. We can say list 2 is greater than 2. And what this is going to do is it's going to return us a new array of the same size as list 2, but with true false values filled based on this condition. So if the item in list 2 is greater than 2, it'll be true. If the item is less than or equal to 2, it will be false. And I think if we run this, it's already been run, but run this, we can see that it's true, false, false, true, true, because we have 5 is greater than 2, 1 and 2 are less than, and these are all greater than. That can be useful if you're trying to look for particular things in an array. Yeah, and another cool thing is that you can index into multiple parts of an array with a Boolean with a Boolean array. So once we've created this array, we can index back into list 2 with that same array, and it'll give us back only the true values. And there's a similar thing here. Yeah, so again, I've said before that arrays, NumPy arrays only will store one type of data in the array itself, unlike Python lists. So here you can see when we print the data type of an array, we'll get, so for this case, we're putting in integers, it'll give us int32. Here we've put an integer and a float. And so NumPy is going to resolve that to the to the data type of the highest precision. So because float is more precise than int, it's going to say that, oh, this is just a float. Or like we're just storing floats. So I can say 1, and I can say 2.0, and then 3 and 4, but those will all just be stored as floats. And you can also specify specifically using the D type argument to say specifically what kind of type you want it to be. And there's a bunch of different things here we've specified as a 8-bit integer. But yeah. Yeah, some basic array math. You can add arrays. So this isn't concatenation like we've seen earlier, but this is just element-wise addition. So it will just basically add, if these two arrays are of the same shape, then it will just literally go element by element and add each element together. And the same thing here, you can use np.add to do the same thing. Same thing with subtraction, multiplication, and division. With multiplication, you can do matrix multiplication, though I think you do have to use a function for that. Otherwise, everything is going to be element-wise. So that's in contrast to something like MATLAB, where if you did something like that in MATLAB, it will try to do your it'll try to do matrix multiplication, I think, before it does element-wise multiplication. So it's the opposite here in Python. Yeah, some more things. These are things that we've probably that are sort of shown in the documentation. So we can do things like summing along different axes, finding maximums, finding minimums. We can also reshape arrays and ravel arrays. So again, I mentioned those before. Reshape is just takes an array and puts it into a particular shape if the number of elements agrees with that. Otherwise, it's going to throw an error. And ravel is just going to flatten it out into one dimension. But yeah, that's sort of it for NumPy and Jupyter Notebooks. Let me go back to the presentation. Is there anything else? It's not. I'm out of slides. We'll go back to the that's the attendance form. If you haven't signed the attendance form, please sign it. But thank you everyone for who's there. I don't know if anyone is there. Is anyone there? Hello? Or am I just speaking into the void? This is so sad.
The void.
The void. Fun. Yeah, that's it. Sign the attendance form. We don't have any other feedback forms or anything. That's fine. I think we're sorted. And pause the recording. Goodbye, everyone.